thank you for the introduction. So session types is a type system for communication channels. And in this talk, you're going to see two channels. On top, there's the main channel. And on the bottom, there's the side channel with my secrets, which you probably can't read in the back. But it's OK. It's just for me. But let's get to the top part. So a session type comes in usually in two guises. Namely, you have one. The first type is about sending message of type T and then continuing as type S prime. And the other one is about receiving a message of type T and then continuing as S prime. Now, most session types system also contains some sort of branching construct. So the branching construct means you're a client that is able to select from a couple of different continuations, which are these SI. And then on the server side, you have a corresponding choice type, which means you're waiting for the client to select one of the possible continuations, and then the server can react on that. So, right. But if you look a little bit more closely to it, you'll see that there is duplicated functionality. Yeah, so here the send operation and here the select operation, both of them are actually sending a message, and then the select information, the select operation does something extra. Similarly, here the plain receive and the choice operation, so both of them are receiving something, but the choice operation does some extra work. So, so you can see with that there is some sort of entanglement going on where communication and the dispatch on the value of the communication are mixed up together. So what we want in this work is actually to disentangle this communication and the dispatch on the communicated value with the goal of obtaining a smaller calculus where you essentially just have one communication reduction. At the same time, we would like to preserve wire compatibility with existing code, where the existing code encodes the choice by just sending a token and then reacting to that token. Before I get into the details of our approach, I will tell you a couple of extra results that we get out just by using this approach. Namely, what we get on top is a fairly direct connection between session types and linear types. We also get more flexibility in implementing session types. We will also have a way of getting a type-safe communication for algebraic data types. And last but not least, with a slight extension of what I'm showing you most of the time, you get length-indexed communication. Right. So what's the heart of our approach? Label-dependent session types. So what we're doing is instead of having a plain send and a plain receive operation, now we have dependently typed send and receive operation. Meaning, just for the receive, you receive in a value a message of type T, but then your continuation can actually depend on the transmitted value of X. And similarly also for the sending. Now, in place of the choice and select, we now have a family of first-class label types, which serve as the encodings of the commands. To actually decode commands, we have label elimination, more precisely large label elimination that happens at the type level. Yeah, so this case is just a branch, a case distinction on labels, like a switch in Java. In the standard typing part, we have the corresponding extension where we have standard dependently typed functions and dependent pairs. Notice for the sake of presentation, I'm putting a lot of stuff under the rug, which you can all enjoy in a lot of detail in the paper. Namely, session types are really linear because they are describing channels whose state evolves over time. Therefore, linearity also creeps into functions and pairs if they contain sessions. And moreover, which is more or less implicit in the previous slides, the type system guarantees that dependency only happens on label values. So you have a system that has linear and unrestricted types, and then just enough dependency to get off the ground and to get this wire-compatible encoding that we were after in the beginning. All right. So now the plan for the rest of the talk is essentially to tick off the points that I had on the slide in the beginning, illustrated with a couple of examples. So the first point is about disentangling communication and dispatch using this wire-compatible encoding. So the first line is about transforming the type of the selection. So the type of the selection really means, no, it doesn't do the right thing. No, it does it. Okay. So the selection really means, let's send a command of type, well, one of the labels that are possible, and then depending on whatever that command was, I'm expecting a particular continuation to happen. On the term level, this is exactly what happens. Yeah, so the usual session type calculi have a sort of select instruction that sends a label on a channel of this kind of offering type. But then in our calculus, this just degrades to the standard send operation. Yeah, so there's no extra operation for sending a label and doing a selection. On the receiving end, it's pretty much the same. So the nice branch type becomes receive a command and then decode the command using a large elimination and then continue according to the selected command. And that's exactly also the implementation. And this is already the heart of this wire-compatible encoding. Essentially what you can do, on the one side, you can have a traditionally implemented session type system that uses the types before the encoding. On the other side of the channel, you can have something that uses our label-dependent encoding. All right. Now I'm getting to the slide, which almost was the main motivation for writing this paper. So if you don't remember anything else from this talk, then this slide should something that you remember. So what you get in our system are these key rules for sending and receiving, which are now the only primitives that you need for talking about session types here. And what you can see here from the typing rule is that the send operation essentially transforms a channel that's ready to send a value of type X, of type T, into a linear function that accepts the value to be sent and then goes to the continuation. Yeah, similarly, receiving here, the receive operation transforms a channel that is ready to deliver a value into a dependent sum where the first component tells you the choice that has been made, the value that has been delivered, and the second one tells you the type of the remaining channel. And this blends in very nicely with existing work by Karras and Fenning and others who also have a whole story built on the connection between linear logic and session typing. And that's very closely related to that. All right, so next I would like to demonstrate the additional flexibility that you get by adopting this label-dependent approach. So here I'm showing you a very well-known example from the literature, the so-called arithmetic server. So this is the type of a server that first does a case dispatch on two kinds of commands, which are neg and add, and depending on which command comes in, either we are receiving one argument and then sending a result, which is like here, or for adding we are receiving two arguments and sending one result. Now the key thing about this traditional session type is that the type structure that we have here essentially determines the code structure. Yeah, so, and I put it here side by side, and I won't really go deeply through it, but here you can see, here we have the branch type that is decomposed by the R case, which receives the command, yeah, and then you have the dispatch on the two commands. For receiving an int, you have a receive operation, sending an int, you have a send operation, etc. Yeah, so that way, the type structure and the code structure are pretty much interlocked. Let's see now what happens if we move to the label-dependent setting. So this is the same type after the encoding to label-dependent session types. So here now the transmission receiving of the command becomes explicit, Now here we have the case dispatching, and the remaining part of the type is pretty much the same. So now, of course, first we can use this type structure again to derive a code structure, which looks like this. Yeah, and here you have the one-to-one correspondence again, as in the previous case. But now, actually, we can be a bit more clever. Namely, we can see that in the body of the case, in the server implementation, we actually have some repetition, and which maybe we would like to pull out of the case. In the traditional implementation with traditional session types, this wouldn't work. Yeah? So it would be impossible to refactor the code. Whereas here, you can just do it like that. You can move it up, and this implementation still type checks against the type without any change. Now, of course, now you can play along. Yeah? So you have fewer constraints on the code structure. Now you can refactor the type if you like to do that. Yeah, by saying, okay, I have to integer receipts here, and I can put it up. So now the types are in sync again, and of course that also type checks. But moreover, and I don't have a slide on that, the type here on the left, this type here, where I pulled the int out of the case, this also type checks against the first implementation before this refactoring here. Yeah, so all that gives you very nice, flexible ways of implementing things. All right. What's behind that is essentially our notion of type equivalence, the conversion relation. The standard thing that you have always in type conversion in dependently typed language is beta conversion. Yeah, and that actually does the alignment, the flexibility that I showed you in detail. In our system, we additionally have eta conversion, and I won't go into the details how that actually works, but that means that you can also do this the reverse pairing between type and implementation that I didn't have time to show you here, but this is also explained in detail in the paper. All right. Algebraic data types, I would love to talk about it because there's a very interesting typing rules here. But in the interest of time, I will just skip on to this part here, which is about net-dependent types. So far, I've told you about the setup for our dependently typed session type system, where we essentially use as index type a family of types L of finite label sets. And then we have the large elimination on labels, which is just the case on these labels. Now, if you want to generalize that to numbers, well, then what happens is that we are adopting as the index type the type net of natural numbers, and the large elimination on labels turns into large elimination of numbers, since we do not allow. This is not a full spectrum dependently typed language. So in the place of the case, we obtain a recursor like you would have in Gödel's system T, for example. All right, so here is an example of the kind of type that you can write now. So here, this is the type of a simple server that first accepts the number of arguments. That's the n here in front. Yeah, so first we accept the number of arguments, and then it has a recursive type, which essentially says, depending on the n describes the number of items, the number of integers that I want to receive, and then in the end, I'm going to answer with a single integer. It's probably best if you, of course, the paper contains all the details. It's probably best to look here at the examples. If I instantiate n to 0, then the recursor evaluates to, on the type level, evaluates just to send an integer and end. Similarly, if, for example, I instantiate n to 2, then the successor part of the recursor unrolls twice, and we get this type where we receive 2 integers, send 1, and then finish the conversation. On the next slide, I'm going to show you the code. It's not for your consumption right now, but if you want to play with the implementation, then you'll see this is exactly what is implemented, and you can also see that the structure of the code pretty much aligned. So here you also have a recursor at the town level, and here you can see the sending that corresponds to the sending in the type. Here you have the receiving that corresponds to the receiving here in the type. And essentially the information that is on this slide is enough to type check the whole program. Yeah, so that's all information that is needed. The pleasing thing is that now you can write a client like I've shown you here on the left. So the client is typed with the dual of the sum server, which is like just flipping sending and receiving instructions. But here you can you can specialize it by saying, okay, I'm just sending the number 2, then I'm sending 2 arguments, and I'm receiving a result. Yeah, and that type checks against this recursor type without any issues. All right. Well, so that brings me already to the end. So the contribution of this work are the following. So the goal was to set up a minimal dependently typed session calculus, which can serve in some sense as a core calculus where you only have just one communication instruction. And the challenging parts in that where we have label dependency, we have linearity, and what I didn't really show you on the slides, we also have subtyping because of the correspondence we have with existing calculi. So that is reified in another technical result where we give a wire-compatible embedding of a conventional session calculus, which includes subtyping and all that, by a type and semantics preserving translation. So then, of course, we have the usual soundness and progress results. Progress, I should say, we don't have any kind of do not prove any kind of deadlock freedom. The soundness is proven as is customary in independently typed settings by proving an agreement result. Then we have shown that type checking is decidable for this language, which requires the main issue in that is to prove that subtyping is decidable in the presence of beta and eta conversion. So that is quite a chunk of the technical development in there. Moreover, we have an implementation of the type checker. The type checker does more than is actually shown in the paper. The type checker is extended to also work with recursive types. If you want to play with it, you can check it out at this GitHub page. And with that, thank you for your attention. You have to wait.
Yeah. So great work. I had 2 questions, and you answered both partially on the last slide. So, and there's always a trade-off between the expressivity of the types and the complexity of the type checking. So I was wondering, I mean, you already said it's decidable, which is a great result, but yeah, is it like, how fast is it in practice? And the second question was about the deadlock freedom. So you said you didn't prove it, but you would still expect to have it, right?
Okay. So let me first go to the first point. If you look at the system as it's described in the paper, I shouldn't say linear, but I mean the type checker doesn't involve any sort of unification. So it's pretty much bounded by the size of the types that you have in the system. So in practice, it's very, very fast. If you use the actual extension with recursion, then you may have unfoldings going on, and then it's probably much more expensive because there's the usual encoding of a co-inductive judgment in an inductive style implementation with caching. So that's going on. The second part, so the calculus as it is not deadlock free. So what we proved is that there is some sort of normal form into which you can get using progress. What could be done is using ideas from other work. If you tie the construction of creation of a new channel to the to forking, then I'm pretty hopeful that you could prove a deadlock freedom result for that kind of calculus.
So very quick question about the syntax. So you are sending singleton of the label. You write parenthesis li, but it is sending singleton, right? And it's syntax of type.
You mean here?
No, not this. Very beginning.
Very beginning, yeah.
A bit confused by syntax.
Yeah, that's true.
Yes. So
Like
this is a singleton.
No, this is not a singleton.
Okay.
No, so in the paper, I have bars over that. So this is meant to be the type that contains a finite set of labels.
And
finite and non-empty.
Because when you have eta equality, you put the bar in the top. So this is a set of set.
In the eta equality, okay.
Yes.
Let me go there.
So I'm a bit confused because.
Yeah, I should have used the bars throughout. So this, oops, no,
yes.
This means X has type label set where the label may be one of L1, L2 to Ln.
Okay.
So this is not a singleton.
Okay.
Yeah. So then the transformation down here says here in A I may have a free occurrence of this variable X. I mean, otherwise I don't need to do this whole stuff. In A I should have a free occurrence of X. And then I'm eta-expanding that to case X of, and then for each label here, I have one copy of A.
Okay.
So that's what the rule says.
And
then due to the way that the system is set up, now you can do type level reductions in A, because now you know if you're in the branch for L1, then you can do the reductions for L1.
Okay, so another quick question is decidability of this indexed type, type checking. You need to then annotation for the program processes.
You need
type annotation for.
You need to annotate the binary occurrences of the variables.
Okay,
yeah.
I see.
Yeah.
Thanks.
Next time to speak again.
Okay.